Now let's consider the principal species. Okay, principal species is what? Is a major species in a given condition. Okay, for example, uh, the dissociation of this weak acid. Okay, and it dissociates to proton and A minus. Okay, yeah, and when um, the solution pH is quite high, mm, no? Although there are three species, okay, two species, HA and A minus, but under the very basic condition, A minus is major species, yeah? And we call it principal species. All right. Mm. Okay, here is an example of benzoic acid. Okay, at pH 8.0. Which one is principal species? Okay, benzoic acid, structure is like that. pKa is 4.2. All right, and using this Henderson-Hasselbalch equation, we can calculate uh, the, uh, the ratio of A minus and HA. Okay, and here uh, when pH equals pKa, this ratio must be 1. That means the concentrations of HA is equal to concentration of A minus. Okay, in the case the concentrations are the same. Yeah, but if pH is uh, less than pKa, yeah, and then which one is principal species? This one. Okay, HA concentration is higher than A minus. Okay, so major species HA. Yeah? Likewise, when pH is greater than pKa, the major species A minus. Okay, this is a monoprotic acid case. And what about the diprotic acid case? Since we have two equilibrium constants, okay, K1 and K2, okay, and we apply the same Henderson-Hasselbalch equation to this case. Okay? When pH is smaller than pK1, the major species is A2A form. Okay, but pH is greater than pK2, and then major species A2 minus. Okay, but in between, between pK1 and pK2, no major species HA minus. Okay, yeah, it's quite simple. So okay, we can illustrate, yeah, on this, you know, this kind of rod. All right, here this x-axis is pH. Okay, and this point is pK1, and this one pK2, and this pK3. Okay, below pK1, the principal or major species H3A case. Okay, this is now we are considering triprotic acid H3A, and between pK1 and pK2, H2A minus, this is the principal species, and between um, pK2 and pK3, H2 minus is the principal species, and beyond pK3, A3 minus is the principal species. Okay, so systematically we can say which one is the principal species. Okay, very simple. Okay, now take a real example. Okay, um, this is arginine. Okay, this is arginine. This is one of the amino acids. Okay, um, this structure is rather complicated. This is what, 1, 2, 3. There are three um, protons that could be dissociated. So this is triprotic acid. Okay, so there are three p values, pK values, pK1, pK2, and pK3. Okay, so the pK1 is 1.82, pK2 is 8.99, and pK3 is 12.1. Okay, in other words, we can write this way. All right, and the question is, what is the principal form at pH 10? pH 10 is between pK2 and pK3. So this one, HARG, okay? Monoprotonated arginine is the principal species. We can calculate, yeah, from this Henderson-Hasselbalch equation, okay? So since pH is 10, so 10 is between this one, pK2 and pK3. So which species is involved? Okay? Uh, this one and this one, all right? And 10 equals 8.99, okay? Uh, 10 is here, so this one and this species involved. 10 equals 8.99 plus log of what? This one. Uh, 10 is between this one and this one, so yeah, these two species, yeah, these two species involved. You see? I'm sorry, yeah, these two species involved. Okay, monoprotonated arginine divided by protonated arginine. Okay, in this case here, all right, yeah, this one and this one. I'm sorry, not this one. Of course not, right? This one and this one. And then we can calculate the ratio of these two species, which is 10 to 1. All right. So, there are some amount of diprotonated arginine, but the monoprotonated arginine concentration is about 10 times higher than this one, diprotonated arginine. Okay. Yeah. Because 10 is what? Uh, 10 is more close to which one? This 8.99. Uh, then this one, okay? Yeah, 12.1, okay? Or this one, 1.82, okay? So in this case, this one, monoprotonated arginine is the major species, okay? Yeah. So diprotonated arginine is the principal form in the pH range of 1.82 to 8.99. Okay, yeah. Which is the second most prominent species at pH 6.2. What is the second most prominent species? All right. Here, let's look at this figure. This is arginine case. All right. And here there are 1, 2, 3 forms. Okay, this one below pK1. This is a major or principal form or predominant form. Okay, between pK1 and pK2, this form, and between pK2 and pK3, not this form, and after pK3 and this form. All right, and here the arginine. Okay, uh, so between this one pK1 and pK2, this form is the principal or major species. All right, and then it says, question is that which is the second most prominent species at pH 6. All right, pH 6. And first let's calculate pH of diprotonated arginine. Yeah, using this one, this very simplified, the equation, and then we can calculate the pH of 5.4. Okay, and then what? Which one? Yeah, this one is the major species, and then second prominent species is what? There are two possibilities. Okay, monoprotonated arginine or polyprotonated arginine. Okay, and monoprotonated arginine is what? So we have to calculate the distance between, the this pH and this our what the pH is 6. All right. So here, let's look at this figure again. Okay. Now we uh, between pH 1.8 and 8.99. Okay, this is the major species, and then since our pH is fixed at 6.0, okay, this is about 9, and this is 1.82. 6.0 is here. Okay, this is much closer to this pK2. So next principal species is what? Must be this one, this form. Okay, this form, not this form. This is a major species, and now you calculate the pH difference between pK and your our pH, right? This one is third prominent species, because this here is a 6 and this is 1.92, and the distance is very large. Okay, yeah. So above this one 5.4, this is the intermediate, the middle point is 5.40. Okay, and then above this one, and then second principal species is what? This one. Okay, monoprotonated arginine, and below this 5.4, and then this form, in this case polyprotonated arginine form is the second prominent species. Okay, yeah, here is a summary. So once you know the principle, and then you can easily identify which one is the most prominent, okay, the major species, and then the second major and third major. Yeah, it is very easy to identify. Okay, and now the topic is fractional composition equation. Okay, now uh, we define the fractional composition. Okay, fraction is what? Total amount. Total we set at one as total. Okay, um, fraction, and then we calculate each species, how much contribute. For example, let's take an example of weak acid. This one in solution, except this proton solution, this weak acid form exists only in two different forms. First one is HA, okay, not dissociated form and dissociated form. Okay, and we want to calculate at a given pH the portion, which is fractional composition of each species. Okay, it is not easy, not difficult to calculate theoretically, and then we write Ka for this equilibrium. Okay, here, and then from mass balance. Okay, formal concentration is the sum of equilibrium concentrations of these two species. Okay, and then Ka can be rewritten instead of this A minus, we written here, and then we solve for HA here. Okay, HA here, it is easy. It is given by this equation. Okay, yeah, and fraction or fractional composition is given by the what? Uh, this is in the actual definition. Yeah, the fractional composition of HA is the this equilibrium concentration of HA divided by total concentration, which is formal concentration. Okay, like that. And then here we simplify uh, this one for alpha. Yeah, the symbol is alpha, right? Yeah, I'm very sorry. Yeah, it is interrupted. Okay, okay. Again, you see, to compare the how much the in this case acid is dissociated in a given pH. So we have to calculate this fractional composition. Okay, and then here this fractional composition of this undissociated form is simply given by this equation. Yeah? So closer look at this equation is expressed by only proton concentration and equilibrium constant. Okay, there is no initial concentration of HA or F. Okay, that doesn't matter actually. Okay, that's the beauty of this fractional composition. Okay, it means once pH is decided, and then automatically the portion of this one alpha HA or alpha A minus is automatically is decided. Okay, likewise you can derive the fractional composition for A minus. Okay, which is given by this equation, or since alpha HA plus alpha A minus is 1, so you can, once you calculate this one, and then to calculate alpha A minus, and you simply take you subtract this one from 1. Okay, and then it is this one. All right, and this one is all the time holds for this monoprotic acid. Okay, like that. Okay, here in this case this is the uh, curve, this curve. Okay, at a very acid condition, this HA is the major species. Okay, and then if you increase the solution pH, and this one HA form decreases rapidly. In the meantime, the A minus form is increases. Okay, yeah, they are quite symmetric. Okay, at a given pH, at any point pH, if you add, let's say, at pH 4, you add this value and this value, and it is all the time 1. All right. And what about the diprotic systems? And we have three species, okay, H2A and HA minus intermediate form, and A2 minus this form. All right, and then we have two dissociation constants, okay, K1 and K2, and then we can derive for alpha values. So there are three alpha values, okay, alpha H2A, alpha HA minus, and alpha A2 minus. Okay, this is given by this one. Okay, the ratio alpha, for example, H2A is the ratio of H2A concentration and formal concentration, and after some manipulation, you reach this equation. Okay, here is the step. Okay, from using K1 and K2, you can this is formal concentration, this is mass balance equation, and then this each species we express in terms of K1 and K2. Okay, and then this one, finally we get this equation, and then uh, like in monoprotic acid, for this diprotic acid, you know, the all this fractional composition is a function of only proton concentrations and K1 and K2. Okay, you see. So when pH is given, you see these fractions are automatically determined. Okay, this figure shows that. Yeah? So at very acid condition, H2A is major species. Yeah? It maintains, but it slowly decreases as pH increases and rapidly decreases. Okay, and then at very high pH, okay, A2 minus is a major species. Okay, and then in the intermediate pH range, you see this kind of bell shape. Okay, this one. This is intermediate species. Alpha HA minus. Okay, but important is that at any pH, the sum of all the fractional composition gives all the time 1. Okay, oh, I missed 1 here. And this cross section, okay, at this point is what HA and A minus, they exist at a same concentration, and then from Henderson-Hasselbalch equation, in that case the pKa equals pH. Okay, here at the cross section. And for this diprotic systems, we have two of it. Okay, here we have two crossing points here. This one is, first one is pK1. Yeah, pK1 is equal to, here the pH is equal to pK1, and here at this point this pH equals pK2. Okay, yeah, very nice. Okay, so everything is quite systematic. All right, yeah. Here let's derive the general formula for alpha, okay, for this polyprotic acid, okay. From our equations, we can write alpha for HNA is proton concentration to n, okay, divided by D. D is what? D is given by this one. This is a rather complicated one, but it is quite a systematic, okay? Yeah, like that. All right, this one. Yeah, but actually not n. N is 3, maybe 4. Yeah, that's the highest one. But you will see later the EDTA. There is compound EDTA, ethylene diamine tetraacetic acid. In that acid is hexaprotic acid. In that case, N is 6. Okay, but usually N value is 2 or 3. Yeah, that's the most most cases. All right, yeah, like that.